All right, good afternoon, everyone. Welcome to November's First Friday webinar. Today's topic is the Water Energy Nexus, presented by Julie Sinistor from Green Scene in San Francisco. My name is Ariana. I'm the Education Specialist with ISPE, so as always, if you have any questions regarding today's webinar or any of our other education programs, please feel free to reach out to me. I just have a few quick announcements before we get started. The handouts for this presentation are available in the handout section of your toolbar. I've also pasted the quiz link in the chat box for you to reach those. We are having issues with our website right now. We're updating our website, so you may experience some issues trying to follow that link to our website that has the handouts and the quiz on it. I would recommend you accessing them from this toolbar instead. But as always, that link to the web page is in your confirmation email from this morning. Please be sure to complete your quiz by next Wednesday so I can email PDH certificates out as soon as possible. And if you have a question for Julie at any time during the presentation, go ahead and type that in the questions box and I'll read it out loud at the end of the presentation. That's all. So with that, I'll hand it over to Julie.
Thanks so much. And welcome, everyone. Yes, my name is Julie Sinistor. I'm with WSP in our Sustainability, Energy, and Climate Change group, and I'm located in San Francisco. And I'm going to talk to you today about, I'm going to give you a quick introduction to what it is that I do in terms of my team and how life cycle assessment fits into what we do here at WSP, and then I'm going to give you a high-level crash course in life cycle assessment. So hopefully by the end of this you'll understand some of the fundamentals of LCA, and then I'm going to dive into the water energy nexus and how LCA helps us evaluate some of the trade-offs between water consumption and carbon emissions from electricity. So as I said, I work on the Sustainability, Energy, and Climate Change team within WSP, and we do a lot of different things. We're a very multidisciplinary team, and so everything that we do, of course, is related to sustainability, but specifically within product sustainability and LCA is where I sit and do what I do. We work with a lot of different kinds of companies and organizations, from private banks and other sorts of commercial financial institutions to California high-speed rail, to public infrastructure type projects, and things like San Francisco Airport, LaGuardia Airport. We've done whole building LCA, which is something I'm going to explain as a part of the examples of how LCA gets used out there in the world. And I actually started my LCA journey doing biofuels, specifically corn grain ethanol and cellulosic ethanol from corn stover and switchgrass. So I'm very happy to still continue to be able to do that kind of work, supporting clients here at WSP. So that kind of hints at why a different organization might choose to do a life cycle assessment. There's a lot of different drivers out there for doing life cycle assessment. One common one I see is in the world of product sustainability, to drive innovation, to create products that are designed with the environment in mind to increase their overall sustainability, whether it's by reducing their carbon impacts or their water impacts, or designing them to use less energy in their use phase to reduce their impacts, or designing them to be perhaps disassemblable at end of life to recapture the maximum amount of the raw materials in support of things like circular economy. Some folks want to substantiate marketing claims. If you maybe haven't heard of life cycle assessment before, then an example of something you may have heard out there in the world that's related to LCA is when you see a product carbon footprint or a product water footprint. So if it says, you know, this product's carbon emissions are X, they should have used a life cycle assessment to calculate that. Or if they're talking about how carbon emissions or water consumption or some other environmental impact have been reduced, they likely used a life cycle assessment to calculate that. Or if they're saying our product reduces greenhouse gas emissions compared to, let's say, the conventional way of doing things, they probably used a life cycle assessment to do that. It also helps in compliance to certain standards and in greenhouse gas emissions reporting schemes when the emissions from especially goods need to be included in greenhouse gas emissions reporting. So that's why. What about what? What is life cycle assessment? I gave you the textbook definition here. The life cycle assessment is the investigation and evaluation of environmental impacts from a product or service. I like to say that it's a way of summing up all of the environmental benefits and burdens from the production, use, and disposal of goods and services. It's governed by ISO standards 1440 and 1444. There's a couple other standards actually related to carbon footprints and water footprints that are also applicable, but they all reference back to these fundamental 1440 and 1444 standards. And what the standards don't really tell you exactly, they give you all of the the terminology and definitions, but they don't really guide you through exactly how to conduct an LCA. But they do have 4 fundamental phases. The first phase is the goal and scope. Just like in any good scientific endeavor, you need to set forth the scientific question that you're trying to answer with your study, and that's the goal of your study. And then the scope is what all needs to be included in the study in order to answer that question. Where do you need to start and where do you need to stop? Where are your system boundaries? What are you going to include? What is excluded? What are you going to measure and how are you going to measure it? And that sets you up for phase 2, which is the life cycle inventory. This is essentially data collection. So now that you know that you're going to include all the raw materials and transportation and that sort of thing, you need to collect data on all of those aspects. And then once you have all of this data, you put that into a model. You build a model. This could be in a software platform, it could be in Excel, and then you're able to calculate your life cycle impact assessments. So the life cycle impact assessment gives you all of the raw emissions to air, water, and soil as a result of the product system that you're observing, and then that takes you to interpretation where you figure out what does it all mean and did I answer my question. And the reason it has these back and forth arrows between the phases, and I have written here that it's an iterative process, is that at any point in the process you might discover that the data that you need to finish your model do not exist, and you might need to revise your scope or make some assumptions and do some additional sensitivity analysis in order to ensure that your assumptions aren't skewing your results or something like that. And what I also like to say, and somebody told me I should copyright this, is that LCA does not tell you what is better or best. It simply tells you what is. So the results that you get, the environmental impact results that you get, like the greenhouse gas emissions from the production of this widget are 5 kilogram CO2 equivalents, per widget. What does that mean? Is that good? Is that bad? Life cycle assessment doesn't tell you that. It just tells you that the number is 5. It's up to you, the commissioner of the study, and the scientist or LCA practitioner that you're working with to figure out what is good and what is bad, or what is better, or what is best within the discussions with your stakeholders that were hopefully engaged in defining the goal and scope from the beginning. So what is better or best is really up to the commissioner of the study and their stakeholders, whether it's investors, the company, the board, consumers or customers. It might be direct business to business customers. It might be the general public type of customer. That's how you determine what is better or best. LCA simply gives you the tools and the facts and the numbers to drive your decisions. So now you know what it is. Let's dive a little bit deeper into a little bit more like the nuts and bolts of what it is. So you start an LCA by quantifying all of the raw materials and resources that are taken from our environment in order to make things. So the classic example that people think of when I start talking about raw materials and resources is mining, so pulling things out of the ground. But it's important to acknowledge that we don't just take our resources from the ground, we also take them from the air, like the way we get nitrogen for fertilizers out of the air, and we also take them from the water. That might be a resource like fish, or it might be the water itself. We might be taking the water to use, and that's something we're going to talk about more when I get to the part about the water energy nexus. But it's important to understand that we take resources from all different aspects of the planet. We take them from the ground, we take them from the air, we take them from the water. And then we take those resources and these raw materials and we make intermediate materials. So we might mine iron ore, and then we turn it into steel, and then we turn that into rebar, and then we turn that rebar into a building, and then that building has a life, and then something happens to it at its end of life, it's torn down. Hopefully those materials are recaptured and recycled, but perhaps they're not. They might go to some other sort of final disposal. But all along the way, through all of these steps, from raw materials to manufacturing, products and transportation and distribution, and a product's use phase and its end of life, we have emissions. And when I say emissions, people usually think smokestacks and, you know, clouds coming out of smokestacks into the air, but we have to remember that there's also emissions to water. There might be wastewater that's treated or perhaps untreated. There are emissions to air, and there are emissions to soil. Landfill is kind of an obvious emission to the land, so we're putting something into the ground. And from those raw emissions that we get at the end of the life cycle assessment, we can determine the impacts on the environment in a variety of different categories. So we've got these different buckets that we can put the emissions into to quantify things like the total energy demand. We can talk about renewable versus non-renewable. We can talk about the global warming potential or the greenhouse gas emissions. Then there are also other types of emissions that affect our environment in different ways, like they might deplete the ozone, they might cause acidification of water bodies, they might cause eutrophication of water bodies. That's when nutrients like nitrogen and phosphorus are emitted in excess of what the lake can handle, and they cause algal blooms, which eat up all the oxygen and can lead to fish kills and smelly lakes that we don't like very much. They can also contribute to smog or ground level ozone, which is a human health impact. And then we can also talk about water use, water consumption, and water scarcity. And I'm going to dive into these a little bit deeper because we are in this webinar to talk about the water energy nexus. And then there are also some human and ecotoxicity factors that we can calculate as a result of the raw emissions that are calculated when we do a full life cycle assessment. So water footprints and all these terms around water. I wanted to make sure that I make these really clear since we are talking about the water energy nexus. So in life cycle assessment, we have very specific definitions for water use, water consumption, and water scarcity and a water scarcity footprint. And these definitions may vary from some of the definitions you may have heard more colloquially or perhaps in other areas of sustainability and sustainability metrics. But in life cycle assessment, water use is the gross amount of water, all of the water withdrawn and input into the process or the system, regardless of what happens to it at the end. So this is a way at getting at what is the total amount of water required, no matter what, for this process. And then the water consumption goes a little deeper. It's the net consumption of water. So it's the inputs less the outputs. So if, as a result of this process, water is taken in, but then it's returned to the environment from whence it came in a usable form, then it's considered that it was not consumed. So if it was consumed, then a variety of things may have happened to this water. The water may have been physically incorporated into the product. So a classic example of that is water bottles. You know, you put water in a disposable water bottle, you seal it up, and that's your product, and it gets shipped off. And so water consumption has to do with the region in which this water was withdrawn. So if you're taking the water and you're putting it in a bottle and you're shipping it off, that water is no longer available in the watershed or ecosystem from where you withdrew the water. And that's important, as you'll see, from a geographic standpoint, to be able to look at where water is being consumed. From an energy generation standpoint, another type of consumption is evaporation. So if water is being evaporated, for example, in a power plant to turn turbines to generate electricity, it's going up into the air, and it is nearly certain that this water vapor will travel far enough away from the watershed from whence it was withdrawn, such that it may rain down somewhere else, but it will not rain down back from where it was withdrawn, and it is not likely to recharge the groundwater or surface water or other reservoir of fresh water in that region. That's very crucial to understand when you talk about the water energy nexus. So some common examples of this, other than a power plant that's, say, burning coal or natural gas, or using nuclear to evaporate water to turn turbines to generate electricity, some other ways in which power plants can consume water is if they have any kinds of wastes, tailings, or cooling ponds. In the case of nuclear, they are using that water and they are making it unusable for other uses. That's not to say that there isn't a possibility, a potential that that water could be cleaned back up and used again, but in most cases, they're rendering that water unusable for other uses. And that's another way in which water can be consumed. It's no longer available in a usable form from the watershed from whence it came. And then finally, another really important one to think about is in terms of hydropower, when you're talking about dammed hydropower. So if a dam and a reservoir are created in order to generate electricity through hydropower, as opposed to another way in which hydropower can be generated, which is called run of river, which does not require any damming. If a reservoir is created, you suddenly create this very, very large amount of surface area that can lead to a lot of evaporation over time. And that's another way in which power plants can consume water. So keep these in mind as I move forward and talk a little bit about, well, towards the end, talk quite a bit about some of the interesting trade-offs in the water energy nexus that we need to think about, especially when it comes to power generation. So finally, I want to talk about water scarcity and a water scarcity footprint. That's the smallest concentric circle here. So water scarcity takes the water consumption, and again, this is why where the water is being consumed is so important. Water scarcity is a way at getting at not just how much water is being consumed, but is it being consumed in a place that is experiencing water stress or water scarcity. And there are a variety of different reasons why an area might be experiencing water stress or scarcity. So first off, the obvious one, they might be going through a drought. They might have limited supply. There can be other reasons why they would have limited supply, but the other reason why they might be experiencing water scarcity is that there could be a very high demand on the water resources. There could be large human population centers, metropolitan areas. There could be industries that require a lot of water and perhaps a lot of very clean water. And then the double whammy would be both of those things happening at the same time in the same place. So a large demand for water from population and industry, and a limited supply perhaps from drought or some other circumstance. And so the map that I have here is called the Aware Characterization Factors for Water Scarcity, and you can see a publication about this, Boulay et al. 2017. But what they did is they went through watershed by watershed throughout the entire world and characterized the level of this water stress for water scarcity footprinting in the world. And these data are actually available in a Google Map layer, so that if we quantify, if we're very careful in our LCA about how we quantify water consumption and where it's happening, we can then apply a scarcity factor to look at this product or service, let's say the product is electricity, and determine not only what amount of water is being consumed, but is it contributing or exacerbating water stress or water scarcity in the place where the activity is occurring? So I know this is a very long explanation, but I think it's really important to understand this very regionalized way of looking at things, because I know I get a lot of questions about, well, you're evaporating the water, but you're not like destroying it, but you are removing it from where it was. And if you're doing that, that could have some impacts on that specific location. And that's a very different consideration from greenhouse gas emissions, which are generally treated globally in terms of a greenhouse gas emission emitted anywhere in the world contributes to climate change, and that affects us all. So where exactly that's happening does not correlate to the impacts that that exact location may experience, and that causes a whole bunch of other issues and problems. But with water scarcity, it can be a very specific and regionalized effect. So not to belabor that point too much, but it's important to understand for our water energy nexus discussion. So jumping back into just what is LCA, as I mentioned, there are a lot of different ways that LCAs can be applied, and one of them is to do a hotspot analysis. So in a hotspot analysis, you can look at, for example, the different life cycle phases in the production, use, transport, and final end of life or disposal of a product or a service. Now, I totally made these numbers up. This is for a completely fictitious product. But what I want to illustrate is one of the reasons why it's really important to look at multiple impact categories in a life cycle assessment is that, let's say you're trying to reduce your greenhouse gas emissions and you're trying to figure out which aspect of the product's life cycle, which phase has the greatest impact on that. Well, if you look only at greenhouse gas emissions, you'll say, aha, use phase has the greatest greenhouse gas emissions impact, so let's target use phase to reduce our greenhouse gas emissions. But what you might not know if you only look at greenhouse gas emissions is that some other aspect of the life cycle is driving a water consumption impact. So in this case, manufacturing is consuming a lot of water. So let's say a designer comes up with a solution to reduce use phase energy, but it requires a lot more machining or energy intensive processes or something like that in the manufacturing phase. What you might inadvertently end up doing is increasing greenhouse gas emissions or water consumption or some other impact in another phase of the product's life cycle while trying to reduce or optimize the one impact category in the one phase. So it's important to look at multiple phases, and it's important to do these sorts of hotspot analyses and look at different alternatives for making changes in the product's life cycle to avoid unintended consequences or trade-offs between other impacts. Similarly, an interpretation may conduct a comparative analysis. So you might look at 3 different solutions. In this case, I have a graph here for a ballpoint pen, a felt tip marker, and a pencil because they all accomplish the same function, which is to make a visible line, let's say, on a piece of paper. I totally made up the numbers for these bars, so I'm not saying anything about pens or pencils or markers. This is just for illustrative purposes. So let's say, again, let's say you only looked at greenhouse gas emissions. Then you would conclude that the pencil has the lowest greenhouse gas emissions, so that's the choice that you should go with. But if you look across multiple impact categories, then you might see, aha, the pencil has really high water consumption. So, you know, again, it depends on what your stakeholders and your customers, what their priorities are in terms of environmental impacts. Maybe they don't care about water. But it's becoming more and more common that folks they not only do care about water and greenhouse gas emissions, but they care more about products more holistically. And so in that case, if you wanted to minimize water consumption, you'd go with the ballpoint pen, but that's the one that had the highest greenhouse gas emissions. And so what often we see in life cycle assessment results is that no one solution optimizes across all impacts. I mean, rarely it does happen, or at very least it optimizes across all the impacts that maybe people care about because those are the ones they really understand. But you know, if you want to go sort of middle of the road on all the impacts, then you pick the felt tip marker. So life cycle assessment, though, again, doesn't tell you what is better at best, but it gives you the information that you need to make an informed choice or decision. And then finally, critical review. I get this question a lot about, well, you know, you could put this study out there and it can say all these things, but how do you know that it's accurate? Well, if the results of an LCA are intended for external disclosure, that would be a yes on this decision tree. And if they are also intended to substantiate a comparative marketing claim, like you're going to say, my widget is better than their widget because it reduces greenhouse gas emissions by X, then the study must go through a third-party, three-person panel critical review. So an independent body of 3 different people with expertise in the field of LCA and the particular product need to review it and conclude that it was conducted in accordance with all of the relevant standards and examine the values to make sure that they are accurate. If it's not to substantiate an external marketing claim that's comparative, so if you're just going to say the greenhouse gas emissions from our widget are X, then it should only go through a 1-person critical review. But in any case, if it's going to be disclosed externally, then it needs to go through some sort of third-party critical review. If it's only to drive internal decision-making, then no third-party critical review is required according to the standards. So this is to ensure the quality and accuracy of the claims that an organization might want to make based on an LCA. So I want to get to some examples of how LCA is used in the real world, and some of the common ones that folks on the phone may be familiar with is what has to do with points that you can get under LEED version 4 that are related to whole building, LCA, environmental product declarations, and regional priority credits. So I'm going to talk about what exactly environmental product declarations, EPDs, and whole building life cycle assessment, or WB LCA are. But essentially, there's a possibility under LEED version 4 to get up to 5 points, or even more if you go for optimization credits, you know, just related to things related to life cycle assessment. So the credits themselves have to do with EPDs in using at least 20 different permanently installed products sourced from 5 different manufacturers that have their own EPDs or some combination of an industry average EPD or product-specific LCA. And there's an additional 3 points available for reducing 3 environmental impacts, including greenhouse gas emissions, by 10% without increasing any of the other required evaluated environmental impacts by 5% or more. So just really quickly, in case any of you are curious or don't know what an EPD is, they're generated from the results of an LCA, and they're based on rules set forward in a PCR. So that sounds like a bunch of alphabet soup. Just to decode that for you, a product category rule is like a recipe that tells you how to conduct an LCA on a product. And EPDs are conducted on all kinds of products, not just construction products like, you know, rebar and concrete and asphalt and flooring and pipes and chillers and doors and that sort of thing. But a lot of other products also have product category rules and EPDs, like consumer electronic goods and that sort of thing. But essentially the product category rule is like the recipe, then the life cycle assessment is like the method, actually, you know, baking the cake, and then the environmental product declaration is kind of like the nutrition label, but instead of saying things about, you know, fat and protein and carbohydrate and calories, it quantifies for each individual unit of the product the greenhouse gas emissions, the water consumption, the waste generated, the energy used, so on and so forth. So this is a practical way in which life cycle assessment is used out there in the world. Similarly, whole building LCA quantifies the environmental impacts from the materials used in new construction in their structure and enclosure. So you can see how having EPDs for these specific products used to build the buildings would be really useful if you were doing this whole building LCA. And these are the categories that are taken into account under the LEED scheme. And as I said, in order to get this credit, you have to reduce global warming potential and 2 other categories by 10% without increasing any of the other impacts by 5% or more. And then the optimization credit is actually to reduce all of them by 10% or more. So finally, we have arrived specifically at the water energy nexus. take a little drink of water because we're going to talk about water. So what is the water energy nexus? I'm sure you've heard of it before. It can be kind of a complicated and confusing term, but essentially it's the relationship between the provisioning of water and the provisioning of electricity. So, and this can go both ways, and this is why it gets kind of confusing. So you could talk about questions like how much water is used to generate and transmit energy or electricity, but you could also talk about how much energy it takes to collect, clean, move, store, and dispose of water. And you can also talk about trade-offs between greenhouse gas emissions from the energy being used to, for example, collect and clean and move and store and dispose of water, but you can also talk about the water that gets used or consumed in the generation of electricity. And so a lot of the discussion that I have heard historically around the water energy nexus has been more about the energy and therefore the greenhouse gas emissions from the provisioning of water. That's a big topic in, for example, the state of California. But what's interesting to me and what some of the organizations that I work with through my job every day are really curious about is how much water does it take to provision electricity? So, and you can talk about this in a variety of different ways. So if you're at all familiar with the greenhouse gas emission protocol, there are these 3 different scopes or buckets in which greenhouse gas emissions are classified. So you've got your scope 1, that's your direct greenhouse gas emissions from your direct operations, and that's usually, let's say your organization owns and operates a factory and you do manufacturing. So if there's any fuels being combusted on site or for, in boilers or in equipment and machinery and that sort of thing, those emissions that come from the combustion of those fossil fuels, that's your direct greenhouse gas emissions. But then you can have your scope 2, which is your indirect. So this is not happening specifically on site at your facilities, but it's happening as a result of your activities. So your manufacturing facility uses electricity, and somewhere that electricity is being generated with a mix of grid sources, but some of them are likely fossil-based, and there are emissions associated with that. So that's your scope 2 greenhouse gas emissions. And then your scope 3 is pretty much everything else. So the greenhouse gas emissions associated with the products that you use to make your product, all the inputs and things like that. And then additionally, things like employee travel and business travel and other goods and services related to your organization functioning. So that's scope 1, scope 2, scope 3, greenhouse gas emissions. What is less clearly understood and quantified, though increasingly becoming important to quantify, it has been your scope 1 and scope 2 water consumption. So it's pretty straightforward to think about your direct water consumption. So you have your manufacturing facility and you're consuming water maybe because your product contains water, or there's water steps, or there's chemical steps that happen in solution, and or there's water being evaporated, and so water is getting consumed on site directly, and that's generally pretty easy to quantify through water metering, wastewater production and tracking in that way. What's a little less clear on how to quantify is your indirect or scope 2 water. And this is actually a blog post I wrote recently about some work that WSP and the World Resources Institute, or WRI, is doing on this scope 2 water is initially why I was even invited to come talk to you today about the water energy nexus, because we're seeing increased interest in being able to quantify this scope 2 water. So scope 2 water, according to the definition that we're working on, would be the water required or essentially embedded in the electricity generated for, again, going back to my example, your manufacturing facility, or in cases of other types of organizations, it might be your offices that you manage or other facilities are all using electricity, and that electricity is using water, and so how do we quantify what that water is? And again, what are the trade-offs between greenhouse gas emissions and water consumption? So we started doing some work into looking into this, and we found some data sets to help us to be able to quantify the water embedded in power and to look at how it compares to the greenhouse gas emissions. So this map, the colors indicate the intensity of the water consumed in generated electricity across the 26 E-grid regions in the United States. Those E-grid regions are abbreviated on the map by their standard acronyms. And then the little pictures trying to look like two little smokestacks. The size of those pictures indicates the greenhouse gas emissions associated with a kilowatt hour of electricity generated in that specific E-grid region. And from this, some pretty interesting conclusions arise just immediately. So, you know, there are some regions with low greenhouse gas emissions that have high embedded water in their electricity. So the one that popped out to us was this Northwest region. So it's dark blue, which means we've got pretty high water consumption per kilowatt hour, but it's got a small greenhouse gas emission. I think it's this second level here. In the legend of the icons. And so what's going on here is that there's a lot of hydropower in this Pacific Northwest region, which is very low in greenhouse gas emissions because there's not fossil fuels being burned to generate that electricity, but it is a lot of dammed hydro, which means that we've got a lot of evaporation coming off of reservoirs created in order to have the hydroelectric dam to generate the electricity. Similarly, we've got some other interesting trade-offs going on. If we look at this SRMW region, we've got a very light color. It's the lightest color on the legend, but we've got a very big icon, which means that there's a lot of fossil fuel generating types of electricity generation going on here, like coal and natural gas and that sort of thing, which don't consume as much water, but have higher greenhouse gas emissions going on. And then we've got some places that are kind of middle of the road on both. I'm out here in California, so my eye obviously goes over to where I'm consuming electricity, and in the CAMX region, we've got you know, middle of the road, but maybe on the lower side of water consumption, and sort of middle of the road on greenhouse gas emissions. And I think a lot of this is driven by methods of generating power that are low on both of these impacts becoming an increasingly large fraction of the California grid mix. And that has to do with renewables like wind and solar and geothermal, and also some methods of generating power that don't produce a lot of greenhouse gas emissions and don't consume a lot of water but aren't traditionally considered renewable, like nuclear. So looking at the data in this sort of way, from a life cycle perspective, these data were all generated using life cycle inventory data, illuminate some of the trade-offs between embedded water and greenhouse gas emissions in electricity. And then finally, just to give you some perspective, and I do want to clarify that the values, let me just jump back here, the values used to generate this map and the values here in this table that I'm showing you, this is both the direct water consumption on site at the power plant, but it's also the water consumption for the upstream of the power plant, no matter what kind of power it is. So upstream, in terms of something like natural gas or coal or nuclear, has to do with the water that's consumed in order to create the fuels. So there is water that's being used to mine coal, to refine nuclear materials, and to extract natural gas, especially through fracking. But also, there is water that is required and consumed for creating solar panels for PV and for creating wind turbines and so on and so forth. So just to give you some idea of the water embedded in electricity generation, we're looking at this, cradle to grave from the generation of the electricity. So as you can see from this table, the lowest water consumer, the lower ones certainly are the wind and the solar. And then in the middle, we have a lot of the conventional fossil type fuels like the natural gas and the coal and the lignite. And then the highest water impact is actually the hydro. And again, that comes from that evaporation. And I have a citation if you're curious to know more about why hydropower has such high water impacts. In this particular data set that I have, this does include run-of-river and storage and pump storage types of hydro, but the most dominant type, especially in the United States, is that storage with the open reservoir. And I know that there are a lot of discussions and debates about the many uses of hydropower dams and how there's recreational uses and there's wildlife uses and that sort of thing. And we can have a discussion or a debate, if you'd like, about how the water impacts are allocated between the power that is generated and the other uses of the dam, like for recreational fishing or something like that. But fundamentally, the reason that the dam was put there was to generate hydropower, and that's often a large economic driver. Even if the power is not very expensive, a lot of it is being generated. It's the dominant economic driver for the existence and maintenance of the reservoir, more so than some of the other reasons for the reservoir existing, which also can be very difficult to quantify in a comparable way. So with that, I wanted to make sure there was plenty of time, and I think I've still got a good 15 minutes for questions. So I'd love to hear your questions, comments, thoughts, discussion.
All right, so we do have a few questions. 1 second, let me pull this up. Okay. When an electric car company does an LCA study, how do they calculate carbon water footprint when electricity can come from fossil, nuclear, or a hydro source? Is by region where car is sold or used?
Yes, it would. If I was conducting that study, that's exactly how I would do it. I would go by where the car is intended to be sold. If it's intended to be sold in a lot of different places, then I would look at any existing sales data about where the cars are being sold, and I would do a sales weighted average of those energy grid mixes. And as you can see, especially from this slide, we can get to some regionalizations in the United States on energy grids. Obviously, some regions are bigger than others, but there are some regionalized values also available for locations in other parts of the world, not just the United States. So we can get at a pretty specific grid energy for things like electric cars. Good question.
Okay, next, what is the difference between PED and GHG?
Oh, okay. So this is going back to some of these interpretation slides I had here. So greenhouse gas emissions has to do with the actual emissions of things like carbon dioxide, methane, nitrous oxide, and over 100 other different gases that contribute to climate change. Primary energy demand has to do with the energy being consumed in order to run the process or create the product. And the thing is that there are ways in which you can generate electricity that do not emit greenhouse gas emissions, like the renewables that we were talking about, or they may have extraordinarily low greenhouse gas emissions like nuclear and that sort of things. And there are also ways that you can emit greenhouse gas emissions that have nothing to do with energy production. A common one is refrigerants. If there's refrigerant leakage or improper disposal of refrigerants, many refrigerants are very potent greenhouse gases. And by potent, I mean they have hundreds or thousands of times the greenhouse gas equivalents in CO2. So one for example, SF6, sulfur hexafluorine, has the greenhouse 2,000 times the greenhouse gas emission potential of one CO2. So, and there are many other ways in which you can emit greenhouse gas emissions, like from agriculture and soils, that have nothing to do with energy demand. So while the two usually track with each other, there can be ways in which they are decoupled. And so we look at primary energy demand, and often we break it out into renewable versus non-renewable to try to understand how much energy does it take to do this process, and then to start trying to target, well, how many phases, how many steps, let's say in the, let me go back to the different life cycle phases. In what phases can we target the use of more renewables, for example? So it might be easier to introduce more renewables maybe on site at your manufacturing facility, and then try to mandate that everything's transported with bio-based fuels or something like that. That might be easier to do and more of a low-hanging fruit than trying to introduce more renewables into the grid in which your product is being used, because that's could be anywhere. Does that make sense? Does that answer the question?
Okay. We have someone referring back to the first question. They're asking, let's see, is it true that life cycle assessment is used in real world applications? Oh, I'm sorry. We'll go back to that one. I want to refer to the first question first. Is that asking for a complete definition to be true, or if it's a component of the nexus? I can go ahead and read the first question again.
Okay.
And then, sorry. Okay. So the first question was, when an electric car company does an LCA study, how do they calculate carbon water footprint when electricity can come from fossil, nuclear, or hydro source? We have someone referring to that question asking, is that asking for a complete definition to be true, or if it's a component of the nexus?
Ideally, it would have the complete definition. Ideally, it would include the scope 1, scope 2, and scope 3, where data are available. But I think that there could be instances where data are not available or they can't be parsed out, and so there are definitely limitations in some LCA studies, and I have seen some on electric cars, but they don't. Some of them don't include the life cycle, the use phase. They only include the production, because they're trying to get at, does producing the car somehow increase impacts compared to producing a conventional car? And then some of them look at very sort of generic energy grids. So they might look at the entire United States energy grid, all averaged together, not broken out by regionality when they're looking at energy.
Okay, Keith, did that answer your question, or should I refer to the quiz? Let me know in the chat box. We'll move on for now. Okay, so we've got another question. Someone's asking, where did you get the data sets you mentioned? And if so, could you give them the sources?
So right here, this will be available in the slides too. The data sets that I use to calculate this and on the map are from the GABI database. This is in the standard professional database for the United States energy grids and all of their subregions, and energy generation in the United States per kilowatt hour for each of these individual technologies. While it is a public database, you have to pay for it, as you do with most curated and maintained, annually updated data sets in lifecycle assessment. So I would refer you to their online documentation for more information about those data sets.
Okay, so I'm going to head back Someone is asking about the first quiz question, and I think that's why maybe we were a little confused.
Oh, okay.
Oh, they're asking for if the first quiz question is a complete definition to be true, or if it's a component of the nexus.
Oh, okay. I need to remind myself, hold on one second, what the quiz question
I'll read
was.
the quiz question.
Because I don't remember.
True or false, water energy nexus describes the electricity required to provision water.
Oh, does it have to be a complete definition? Well, that kind of gets at what the answer is. So yes, it needs to be a complete definition.
Okay, thank you for clarifying that. Yeah. Thanks for bearing with me, you guys, as well. We do have a lot of questions this time, so let's keep it moving. For LCA, does costs mean money or the environmental impact?
Generally, when people talk about costs, they're talking about the financial burden. So what I commonly get confused when I say to people, hey, I do life cycle assessment, I do LCA, they say, oh yeah, life cycle cost analysis, I do that all the time. We do the same thing. And that's a common point of confusion. Not to say that I can't do that, but it is not life cycle assessment, and the standards do not include life cycle costing.
Okay, so it's safe to say that on the quiz question number 2, life cycle assessment evaluates the costs from the production, use, transportation, and disposal of a good or service that you're referring to the financial aspect.
Correct.
Okay. Next question. Is it true that life cycle assessment is used in real-world applications, including credits for LEED v4, such as from whole building LCA and environmental product declarations?
That's question 4. If I answer that, then I'm just giving away the answers to the quiz.
Okay, we'll move on. Your discussion of energy is regarding electricity. Is there similar water energy nexus analysis to be done for energy used for heat, natural gas, oil, coal?
Yes, definitively yes. That is a next step that we would like to take once we finalize this document that we're working on Scope 2 water and electricity. It's been a very heavy lift, a big undertaking to come up with these lists of factors that folks will be able to use to quantify Scope 2 water impacts, and they will be publicly available. We've also gone through the exercise of creating a guidance document on how to use them and how to calculate Scope 2 water, and that has taken pretty much the entirety of 2018 and will go on into 2019 as we engage with stakeholders and advisors to review the document and the factors. So an obvious next step is to start to apply it to energy sources for heat, but we just haven't gotten there yet.
Okay. Why does lignite consume more water than coal? I hope I'm pronouncing that correctly.
Yeah, so this is getting back to, let me just unpause my screen. Oh, I think I actually just stopped sharing. Sorry, but this is getting at the comparative water impacts. I'd have to look back at the data sets, but off the top of my head, I think there's, again, since this these data included the upstream production, I believe that there's more water required in the extraction and production of lignite, the fuel itself. There may also be additional water required due to the differences in how the two fuels burn, required and evaporated to generate the same amount of electricity. There are probably differences in their energy densities.
Okay, it looks like we have one more question. Doesn't California use a lot of the electricity generated by the dams? Has this been taken into consideration when calculating the low greenhouse emissions for the state?
Yes. So the CAMEX boundary is drawn based not on the actual border of California, which is why the top of the map looks all funny when it's kind of a strange meandering border, when by our political boundaries, the top of California is a straight line. And so the US eGrid regions take into account some of the energy trading across boundaries. And there are also hydroelectric dams in the state of California as well that are providing energy to the state, but some of that is also exported as well. So it's a balance though, and that's part of the reason why I think that the CAMEX region is sort of middle of the road on both water consumption and electricity, because we have, and greenhouse gas emissions, because we have such a diverse set of sources of electricity in this state, and we're trending more and more towards the renewables. This does come with a greater reliance on hydro because it's low greenhouse gas, and it's important to perhaps watch this in the future to see if it drives up our water consumption, because we are a water scarce and water stressed state.
Okay, that's all the questions we have. Julie, I just want to thank you for a great presentation. We really appreciate having you here to speak. And thank you everyone for joining us today. I just have a few reminders. A link to the handouts and quiz can be found in the confirmation email you were sent yesterday and this morning. Just be sure to complete that quiz by at least Wednesday so I can email out PDH certificates. If you're strictly here for PDHs, I do want to remind everyone we have an extensive list of on-demand webinars on our website, which includes past First Fridays and some of our virtual bootcamp webinars. We're also going to be having 2 more webinars this month on the 14th and the 28th with Brett Zitney from GeoPeer and Reed Just from Holmes Murphy. The registration for those are available on our website now, so go ahead and check that out. I think that's all I have, so thank you again, Julie, and everyone else for joining us, and have a great weekend.
Great, thanks everyone.